talk about advising soon.
All right. Can you hear me? Sorry, actually.
I'm sorry?
You can hear me, right?
Again, yeah.
All right, thanks. In my last class, my mic wasn't working, so I was just checking.
Yep, yeah, I can hear you. Okay. So let's see here. Yeah, so there's I posted the last homework assignment for the semester. It's a fairly short assignment that'll cover PDEs or differential equations in general, I guess. And that's going to be due currently 5/7. I think that should be sufficient. I'd like to probably hand out the final close to then too, maybe even the class before that. So I'd like to I'm trying to block off the last week or so to just let you work on the final and answer questions and things like that. So that's why I'm trying to make those due before the end of the semester. And then we've got another homework assignment due on this Thursday. That's a Fourier series assignment. I think that's all I really wanted to say, though. I think speaking of registration, I think that started this week, possibly today. Is that right? So keep that in mind as you're keeping track of stuff. You should register for classes for next semester. Thoughts on your mind before we get started with today? So we're going to start with chapter 6 today, the last chapter, the PDE chapter. I keep second guessing myself PDEs. I think there's some just regular ODEs in here. Maybe not. It might all be PDEs. Anyway, this is the last chapter we're going to cover. I had posted the notes a couple weeks ago, about a week ago at least. Hopefully you had a chance to print those out. Anyway, thoughts about anything before we get started with these? Questions about homework or anything else?
Yeah, I had a quick homework question for 6.
Yep.
So for number 2, we're finding the even and odd. So that's just for one of them, we're just using essentially just doing a sine series and then a cosine series, right?
Yeah, right. So there should be a code for each one of those in the Dropbox. I would suggest using Maple as much as you can on this. Okay. I think in one of them I said show your work, but in most of the other ones you can just use Maple. But yes. For number 2, you should have 2 different Maple codes.
Okay, yeah, because one of them is only using I think it's A's and one of the B's, right, or something like that. Because one of them has sines and the other one has cosines, so it's just finding all of them and then putting just the sines in one and the cosines in the other for 2 series. Okay, yeah. Cool.
Trying to remember which one we did in class. Did I accidentally sign this one in class? So just to be clear, when you do x squared on 0, 1, it looks like this. And so the even version of that, we did this in class, but it looks like this. So that's going to be the even one. And then the odd extension would be the one where you copy it and paste it down here. And so it does that over and over, I think, right?
Okay, so when you find the odd with only cosines, it'll look like that. And when you find the even with only sines, it'll look like the top one.
Exactly, yeah. So the even version should end up looking like this, and the odd one should end up looking like that.
Okay.
And there's different ways to do it. I don't remember off the top of my head what those codes look like, whether you break up. I think you define the function at the top, and so this one would just be x squared. Or I guess it would be x squared plus, no, it'd just be x squared, right? And then this one would be like a piecewise function that is x squared from 0 to 1. And then it's, what is it, like minus x squared from -1 to 0, something like that. Other thoughts, questions? Okay. So there's about 20 pages left in this chapter, and I don't intend on doing anything past that. So like I said, I'm trying to stop here close to when we would have normally stopped and give you some time to work on the test, and maybe we can meet during that time And we could like talk about test questions. Okay, cool. So this section is about partial differential equations, which is a huge topic in applied math in general. Like there's huge courses dedicated just to PDEs. When you get to grad school, partial differential equations is like one of the things you can study, like analysis, geometry. I did math modeling, and there's also partial differential equations. And so we're not going to like dig really deep into it, partially because it's a pretty advanced topic that requires real background in analysis to really do the right way. And also, again, just because this is one section of our course. So we're going to derive a few of the key equations. We'll talk about solving some of these and their general solutions. And we'll look at some simulations in Maple. Okay, so let's look at the definition. So first of all, a partial derivative. So when you see the word partial derivative, you should kind of be thinking about what you did in Calc 3, right? A partial derivative of a function with 3 variables, in this case, x, y, z. If we're doing the partial derivative with respect to x, what we do is we take the derivative with respect to x while keeping all of the other variables constant, right? So again, this is something that you would do in Calc 3 or multivariable calculus, if you will. So this is the definition, right? This is the notation. So it says take the derivative of the function f, but we're only doing it with respect to x. Another way to notate this, another notation for that would be just doing f with a subscript x. That means take the function x and take the partial derivative with respect to x. And so the definition looks very similar to the formal definition in calculus, and this is the definition that we looked at when we were looking at the calculus definitions in the Fourier series section, except that we're dealing with more than one variable. There can be any number of variables. In this case, we're just looking at 3 dimensions just to keep it kind of simple. But you can see that the limit here is only with respect to x going to 0, where y and z are just being held constant, right? So in other words, y and z are really being treated like constants in this expression, and only x is a variable that's changing, right? And so this is x changing and going to 0. And when we let it go to 0, it becomes the derivative. And so this would be the partial derivative with respect to x. And we could also have the partial derivative with respect to y, or the partial derivative with respect to z would be similar notations, right? There would just be like a delta y here instead, and this would be a y, and this would be a delta y, and this would be x would be constant, except you'd have y plus delta y, right? So you'd just be the same kind of formulation, just with y's or x's, z's, excuse me. We're not going to deal with the formal definition. I just wanted to relate it to the formal definition, just since we saw it in the last section when we were talking about that Fourier series, those calculus definitions. And so let's just do a quick practice here and remind ourselves how to actually take partial derivatives. So one partial derivative we might want to do, here's a function of 2 variables, x and y. And in some cases, it's just an x. And in other cases, we're multiplying things with x's and y's, right? So if we wanted to find the partial derivative with respect to x, and I prefer using that notation just because it's simpler. You're welcome to write it like this if you want, but I prefer just the simple one. Again, you treat y like a constant. And so we just pretend like these 2 y's don't play a row. It's just like some number or something. We fix them. And we would instead do the derivative of e to the x, which stays the same. We would do the derivative of just x, and so the x becomes a 1, but the y stays the same. And the same thing happens in the other term, right? Because we're just ignoring the y. We're just kind of treating y like a constant. Whereas if we wanted to take the derivative with respect to y, we do the same thing with x, right? So the e to the x doesn't have a y in it, and so that just becomes 0 because we're kind of treating it like a constant, right? In the second term, the y would become the 1 because we take the derivative with respect to y. And then in the third one, we just focus on the cosine part, and so we don't do anything with the x. We just take the derivative of cosine, which turns into minus sine. So I know that's stuff that you've seen before, certainly in multivariable calculus, and I know some folks, I don't know, do you deal with this? Do you do it? I guess the differential equations course we offer is just ordinary differential equations, so maybe you don't really see that in there. So anyway, just wanted to sort of remind you about what partial derivatives are. Thoughts about that at all? Am I remembering correctly that, Danny, are you in Calc 3 now? Are you in that multivariable calculus?
No, I was either going to take that or this, and I chose.
Okay. So then maybe you haven't seen this before then. Is that right?
Yeah, I don't think I've seen this.
Okay. Do you kind of see how that works, or anyone, but specifically maybe Danny, since he hasn't seen this before?
Yeah, it makes sense. Of just like doing the derivative of only one thing while the other ones stay the same.
Yeah. It feels a little bit weird to kind of ignore the variable sometimes. Like if you see x times cosine y or even xy, that sometimes it kind of feels like it should be a product rule because you're multiplying variables. But when you do these partial derivatives, you're just fixing one of them and just pretending like you plugged a number in, kind of.
Right. So I guess yeah. So the only other thing that looked kind of weird was the cosine y. So since it's cosine y, we're saying that whole thing is considered a constant since the y is like a part of it.
Yeah, right. It would be kind of like if we plugged a number into it. Let's say it was like cosine of, I don't know, pi. Like that would just be then a constant. Cosine of pi equals -1, for example. So that would just be like fixing the entire thing.
Okay, so essentially not taking the derivative of that. Since it is what it is.
That's right. It becomes a coefficient, essentially.
Okay, that makes sense.
Other thoughts? Just thinking as I was doing this, I didn't put any of these kind of questions in the homework. If I can remember to do that by the end of the day, I'm sure no one will download it and start working on the homework right away. I might add a couple questions so just to see that people can do a partial derivative. And so we can keep taking derivatives. So the next part is just keeping in mind that higher order derivatives exist for partial derivatives too. So if we wanted to do, for example, fxx, it'd be taking the derivative with respect to x twice. And so we did it once right here. And so it would be just, taking the derivative of the thing we already just found. Right, so we already found this part right here. And so if we wanted to take the derivative again, we could just focus on this and take the derivative. And when we do that, again, e to the x stays the same, but now this 1 times y no longer has an x with it. And so this term is going to become 0. And so is the next term, right? There's no x in the second term either. So, which would obviously just be e to the x. So just kind of emphasizing that you can do higher order derivatives, but the interesting thing with these partial derivatives is, you have more than one variable, so you can kind of mix them up, right? So instead of like fxx, for example, you could do fxy, which would be looking at the thing we found a second ago right here, but then taking the derivative with respect to y, right? So it's like doing the y derivative of the thing we just found. And if we looked at this and did the y derivative, the e to the x would go away, excuse me. The y would become a 1, and then cosine, again, becomes minus sine. Thoughts about those? Folks see what I'm saying there? Okay. So we just did a couple second derivatives of the one we just found, the fx, right? We took fx and then took another derivative. Let's do the same thing with the other one. And I'd like to just make sure that you can try this, make sure you know how to do this. So see what ffy is and fyx. Just take a second. So we're dealing with fy in both these cases. And so take this expression and take the derivative with respect to y, and then x, and just see what you get. There. Again, just want to make sure that this makes sense, and so you can verify your understanding about that. So when I look at the first one and I take the derivative with respect to y again, the x goes away, so it's going to be a couple zeros again, and then this one, the sign becomes cosine. So we'd have minus x cosine y. And the negative sign is just from before. And then if we took that same expression and we took the derivative with respect to x, this one becomes a 1. And the second one also becomes a 1. So it'd be that. And notice that you actually get the same. Well, first of all, is that okay? Any questions about either of those? And so notice that this happened. This thing right here that we got was the same as this one right here. In other words, fxy was the same as fyx. And so that's the theorem that's at the top of the next page. It says it doesn't matter the order in which you take derivatives, the derivatives will commute, is what the thing at the top of the next page is saying. And here's just an example of that happening, right? Doing the derivative with respect to x first, then y, is the same thing as doing y first, then x. So I'm going to flip the page and just look at that for a second. So it's called Clairaut's theorem. Here it is. Sometimes, you know, these theorems and notation can look worse than they are. When I first like relook at this thing, sometimes I'm like, wow, there's a lot of notation there, but it's really not that hard, right? So it says if we have a function with a bunch of variables, so a multi-dimensional function, and we take the derivative at different points, or this vector a1 to an, then this is true. So notice that these two expressions are almost the same. You're taking two derivatives in both of them, but in this one, you're doing the xi first, then xj. And in this one, you're doing xj first and then xi, right? So you're just switching the order in which you do the derivatives, just like we just said, right? In other words, partial derivatives commute. Finally, the final way to say that is what we just showed. fxy equals fyx. I do want to just note, though, that because sometimes I feel like people, especially in this class, get a little confused sometimes. Just showing this one example, showing that fxy equals fyx in this one example is not enough to come up with a theorem, right? So there's some pure abstract proof that shows that you can change the order, and it involves using this definition right here. And I just want to be clear that just showing one example works is not enough to create a theorem. Sometimes when I ask people to prove things, I get specific examples, and that's not an example. And just we illustrated this theorem using that example. And you can see here's just the notation being kind of fleshed out a little more carefully, right? So I'm just going to zoom in a little bit so you can look at that a little bit closer. So this is. Let me let it focus. So this is, you know, when the number in the numerator, like the 2 or the 3 or whatever, that tells you how many derivatives are taken. So for example, sorry, I just got confused here because this one should be a 3. This should be a 3 right here, sorry. That's what got me confused, right? So most of them have just 2 derivatives, which is why there's a squared in the top, and the ones that have 3, there should be 3 there, have taken 3 derivatives. Now, when you take the same derivative a bunch of times, like you take x a bunch of times or y a bunch of times, like in these right here, you just end up with that same power in the bottom because you're just multiplying dx together. But if you, so like, let me just write this one out in detail, for example. This one is like the derivative with respect to y of the function df dy, right? And if you multiplied both those two things together, you'd get a squared in the bottom, and then the 2 in the top multiply to give you that. That's sort of one way to think about those powers. Which is why if you're mixing variables like x and y, you're not going to get the same power on the bottom because you're mixing it up, right? Like this one is taking the derivative with respect to x of this. Okay. So this is just sort of fleshing out the notation. Again, I try to use the notation mostly on the left, the shorthand notation, like with the subscripts. I just think that just makes more sense to me and it's quicker to write. But you should be able to recognize the different notations. Lots of people use the other type for sure. Anything I can clarify there? The last thing I'll just clarify, I should have probably typed this out and I forgot to. Sorry, you'll have to write it down. But it's what the order of a differential equation means. So the order is how many derivatives have been taken. So the order of a differential equation is how many derivatives have been taken. That's like a really common thing to hear, like, oh, it's a second order derivative, it's a first order homogeneous, whatever, right? So we want to be able to nail down these vocabulary. And if you look at the next page is all about vocabulary. I have distinct memories of being, you kind of get scared by vocabulary sometimes if you're in like a talk and someone's like, okay, let me present this third order homogeneous differential equation in, Hilbert space or something. And you're like, whoa, I don't know what any of those words meant. Right, so understanding what the words mean is like the first step in understanding more advanced topics. So anyway, we're just trying to get some vocab under our belt. So anyway, the order is how many derivatives have been taken. So for example, fx and fy are both first order because only one derivative has been taken in each case. If we took two derivatives like xx, xy, yy, yx, these are second order. And you could imagine what third orders would look like. xxx, xyx, ... etc. These would be third order. And that continues forever, of course, right? You can have as many orders as you have variables or more. Right? It's not limited by the number of variables, right? You can just keep taking derivatives. Okay, anything there?
I have a question.
Yeah.
So I guess it's kind of in general with this whole idea. So if you're taking like the partial derivative with respect to x, that's going to be different than when you take it with respect to the other variables. So do you just use whichever one you need to essentially?
Yeah, depends on the application, right?
Or is there a derivative for the entire thing?
Good question. No, yeah. So there's not, when you say a derivative, you're probably thinking about the calculus context where there's only one variable. And so there's only one derivative or one first derivative at least because there's only one thing to take the derivative of, the one variable. And when you do that maybe we should have started there. I should have sort of assuming some people had some background in this. I apologize, Danny. Even people who didn't, usually if you had like something that's a function of time, for example, and I think about disease spread and we're in the middle of a pandemic. So I'm gonna think about that. So this is like maybe number of cases of some disease, and this is time. And the number of cases, usually in epidemics or whatever, they do that. And so in this, when you take the derivative, you're just doing d over dt because there's only one variable. But if you think about what this function looks like, it only has one variable in it, and it's t. And so you couldn't possibly model the number of actual cases of an epidemic using just time. Like the number of cases depends on more than just time. It probably depends on at least time, the number of infecteds that exist, the number of susceptibles that exist, and lots of other things. Let's just keep it at those three things then. And that automatically changes your problem from a 2D thing into one that has time, number of infecteds, and number of susceptibles. And so it creates this three-dimensional thing where we still might have some curve that exists here, but each derivative tells you how the curve is changing with respect to one of the variables. And so they tell you different things. So for example, if we did this would tell you how f is changing with respect to the number of infecteds.
Okay. So essentially, yeah. So there would never be one for that whole thing because there's multiple variables. But doing the partial derivative for each one just tells you something different. So essentially, you don't. So having essentially one for the whole thing doesn't really make sense anyway.
Yeah. Right.
Okay.
So like, if you remember when you do it in a 2-dimensional example, like if this is the point you're taking the derivative at, it tells you the slope of this tangent line. So it tells you how steep the graph is right here.
Okay.
If you do it with a 3D example, like here's a 3D thing. This is my, what is this thing? These are headphones. This is my headphone case. This is some 3D object. If you took the derivative like right here, it would tell you, and let's make this more clear. Let's say that this is X in this direction, Y is in this direction, and then Z is coming off the page, right? So if you took the derivative with respect to Y, say right here, it might tell you the slope of the tangent line going this way because this is like the Y way. If you did it with respect to Z, it's going to tell you that, or X, I mean, it'll tell you the slope of the tangent line going this way. And if you did it with respect to Z, it'll tell you the slope of the tangent line going up.
Okay.
And so it tells you how the function's changing with respect to the different variables, depending on what the context is of those variables.
Gotcha. Okay, that makes a lot of sense now.
Okay, yeah, sorry to sort of jump right in there. Other thoughts about that or anything else I can clarify there? So, we always start with this. Math is hard enough, right? So we start with these one-dimensional things, and it's hard to imagine like everything you've done in math before, and including calculus, has been not enough, right? It's like, wow, all this stuff is kind of hard, but in reality, all that calculus stuff almost never applies because there's usually more than one variable involved in a problem. Like very few real world problems are going to have one variable. And so we start with these sort of simple, quote unquote, one variable functions in most of the classes to build the foundation. And if you like it enough and you keep taking classes, then we add more dimensions and start making things more realistic. The theory still applies is a nice thing. Usually when you get to higher dimensions, it just becomes more complicated because you have more variables. Anyway, a little bit of a ramble there, but other thoughts or anything before we keep going? Like I just remember when I took multivariable calculus, I was like, wow, we're adding this third dimension. And I thought it was so cool that there was I could think of some function that, or I couldn't come up with it myself, but there was some function that existed that you could use to describe shapes, like 3-dimensional shapes, not just these 2D things you drew on a piece of paper. And that really inspired me. I felt like to keep studying math was that I call it Calc 3. We call it multivariable calculus. Anyway, let's keep going with some more notation things, some more notation and examples. So that was actually a good little setup for this page because the first thing we're going to talk about on these definitions and examples are the difference between a PDE, a partial differential equation, and an ODE, or ordinary differential equation. So first thing you should note is just the abbreviation. Very common abbreviations that people in math use. Anytime you're in a math setting and you say PDE or ODE, everyone will know what you're talking about. If you leave that setting, you might have to say those words. But the idea is exactly what we just said. So this kind of concept that I was just talking about with Danny a second ago here. If it's an ordinary differential equation, that means there's only one thing to take the derivative of. And so when we take a derivative, it's just the derivative. It's the ordinary differential equation. But if there's more than one variable and we take a derivative, all of a sudden there isn't a derivative or the derivative. There's one of the partial derivatives. And so that becomes just part of the derivative, right? Or it tells you how the function's changing in one of the directions. And so that's the difference between these two things is with a partial differential equation, it's going to be a differential equation with at least two inputs or variables. Where the ODE, the ordinary differential equation, is a differential equation with just one input. And so when you take the derivative, it's just the derivative. There is only one. And so just, again, think about those examples I just wrote on the last page. But we can also write a couple down too. So for example, a partial differential equation would be fx plus fy equals 0. So when you take the derivative, the partial with respect to x and the partial with respect to y, add them together and get 0, that's a partial differential equation. I'm going to write down a number of them just to give you some flavors here. So here's another one. This is just a first order because there's only one derivative going on there. Here might be a second order because we have two derivatives. And this is starting to look like some of the forms of functions we might see here. I'm going to write a couple more down. That might be a partial derivative. We know it's partial because there's a y right in there, right? So we're doing a partial very clearly. And we can have all different kinds of them here. I'll just write down one more just to write down a third order, right? That's a third order because there's three derivatives. Now that's different from ordinary differential equations because usually when you see ODEs, and we will see some ODEs, we're kind of going to use some concepts from ODEs to solve some PDEs, basically. So we will look at some ODEs. Usually you just see them like, oh, y prime equals sine of x or something like that, right? This is telling you that you're doing the derivative with respect to x, right? Those are the same thing there. And you just know which with respect to x because there's only one variable. So that's why you don't have to write y sub x or something because there's only one variable. You know there's only one variable, right? Or something like this. Right? These are all ODEs. Now, we'll be looking at some that kind of look like this. They kind of look like systems almost. Well, they are systems, really. Or they become systems. Or they're not systems, but they're second order, I guess is what I'm trying to say. Higher than first order. That involve both the second derivative, the first derivative, and actually the solution, right? So here are all three derivatives, or two derivatives in the original function, involved in the same equation. So we'll look at solving some that look like that too. Okay. Is that okay? Thoughts about either one of those? So I know like a couple people took PDEs. ODEs. I know Nick took them, and I think Matt did as well, but he's not here right now. Anywho, let's talk about linear versus nonlinear. So that's ODE versus PDE. We should understand what linear versus nonlinear are, and we're specifically talking about differential equations in this case. So let's define them again. So linear, you probably imagine, means something to do with powers of 1, right? And so that means these are differential equations where the dependent variable, so the function, and all of its derivatives are a power of 1. And so it's easy to see if something's linear because it'll have powers of 1. You can imagine it's also easy to see if something's nonlinear because it's going to have powers bigger than 1, right? So this is going to be the dependent variable and or the derivatives are nonlinear. So power of at least 2. Now, that one's a little harder to see sometimes, at least without what I'm about to tell you. So let me show you just a couple examples here. If this was an ODE, so let's do a couple examples of ODEs, and we'll do a couple examples of PDEs. So with ODE, like a lot of the ones I wrote here were oh, that's right. That's why I wanted to write so many examples up here. I wanted to write enough examples up top here that we could start picking out some linear and nonlinear ones. Do I have enough up here? I'm going to add one more to this example. I'm going to add this one. And then this one. Yeah. I'm going to add one here too. Okay, so out of the ODEs, so I've got 1, 2, 3, 4, 5 ODEs listed right there. Which ones are linear? So I'm going to write down an easy one. This one is linear. Now, I'm not saying e to the x makes a straight line. I'm saying that the powers that exist in this ODE have powers of 1 on the y's, right? So on the y's or the y primes has a power of 1. So what's another one that's in this list right here that has powers of 1?
With the sine x ones.
Yep, the sine one. I'm just gonna. So I just rewrote that one sort of 2 different ways. So I'm just gonna write that 1. In this one, I'm assuming m is just a constant, so that one has a power of 1. And then the one that we really need to start realizing is linear, that maybe doesn't seem like it, is the last one too. Really, the only one that's not linear is the y squared one. So this one is also linear, the y double prime plus 3y prime plus y equals 0, because it satisfies that definition, right? The dependent variable there is y. And so the dependent variable and all of its derivatives have a power of 1. Right, so y prime, and y double prime are all there, and they all have a power of 1. The one that's not linear is this one, because the dependent variable, y, has a power bigger than 1, 2. Right, so this is the part that's messing that one up. All right, what about the PDEs? So what's a linear PDE? There's 2. There's more than 2, actually. There's 4.
First one?
The first one. I'm going to do a quick check-in here. Nick, what's another one? Nick, are you with us? Not sure. Zach?
Sorry, what was the question again?
Which one of these PDEs is linear? There's a bunch of them here, actually. Most of them are linear.
Yeah, I think all of them are linear except for fy plus ftt squared.
I agree. Yeah. So the only one that doesn't have so f in this equation is the dependent variable. And the dependent variable and all the derivatives have single powers except this one because it's squared. Absolutely. So this one, they all do. Oops, not that one, actually. That was the one that was actually a little bit tricky that I lost track of. So that one is not linear. And so I'm going to go ahead and write that one in the nonlinear section here. And it's because of this term. So this is nonlinear because f and fx are both the dependent variables, and they're multiplying them together, right? And so yes, they're different, and so you don't get a power because they're not like terms, but you're multiplying 2 dependent variables, which makes it nonlinear. So that's the kind of term that you really want to be aware is a nonlinear term. I mean, it should be kind of obvious that this term is nonlinear, right? I mean, it's nonlinear because it's got a square. But the power, you have 2 dependent variables. There's one just happens to be a derivative, and so you're multiplying. This one makes it nonlinear. I just wanted to mention that one specifically. Didn't get to put Bradley on the spot, and Nick kind of copped out, so I might have to come back and make sure people are with me here. I'll answer some questions before we just finish this off with homogeneous versus non-homogeneous. Because again, you want to be able to say when someone says, I've got a linear, non-homogeneous ODE, you just in your mind, you should be kind of picturing sort of what that is. Okay, so homogeneous, if you remember your linear algebra, a homogeneous equation in linear algebra was one where you do this. So this made the equation homogeneous in linear algebra. So you have some system on the left and it equals 0 on the right. And so that's the exact same thing in this setting. A homogeneous differential equation is specifically a linear differential equation where all non-zero terms contain the dependent variable. And a non-homogeneous then would be a linear differential equation where at least some, doesn't have to be all of them, but there have to be some non-zero terms that are missing the dependent variable. So in this case, we're only talking about linear ones, and so when we pick some out here, let's just look at the linear ones that are listed right here. And we want to think about linear ones that have the dependent variable in all terms and maybe ones that don't. So again, with the PDEs, the dependent variable is f. And with the ODEs, the dependent variable is y. So thoughts about either one of those? I'm going to do the same thing. Let's write down the ODs. And we'll write down the PDEs as well. Love to hear from Nick or Bradley about this. Someone say something? Sorry.
No, I just no.
Bradley, can you confirm you're with us? She's there. Bradley and Nick not going to throw anything out there? What you got, Danny?
So just in terms of which one of these are homogeneous and non-homogeneous.
Yeah.
So I think for PDEs it would be the first two. So like f with respect to x plus y, fy equals 0.
Yep.
Or equal 0. So would it just be all the ones that are equal to 0?
Let's see here. So this one, both the terms have an f. This one's missing that, right? So this one's out.
Right.
This one also is missing that. But this one also has both terms being f. So it's just these two.
Okay. Oh, because it's like, right. Because
so like this one goes down here, for example, because this part doesn't have an f or a derivative of f.
Okay.
And then the other one, those two terms are fine, but then this one doesn't have an f.
Okay, and what was like and that's just because since it doesn't have an f, it's not just respect to each other essentially equaling 0. You have something that's different.
Yeah, like if you're thinking about the functions or their derivatives, this is sort of a constant in that respect. Yes, it has variables y and x, but it doesn't have the function or its derivative. And so if you're thinking about the function and derivative, these things they're not constants, but they're sort of constants, quote unquote, with respect to the function and derivative.
Okay. Whereas like the ones under the PDE for homogeneous, it's two functions with respect to their
you have derivatives of the functions in that one, and both those there. That's right.
Okay.
And And so then with the ODE, then I'm looking at these ones right here, and the only one that has all, y is the dependent variable. Excuse me. And so this one definitely is in. Right, each non-zero term has a y, for example.
Right, because even though we're not talking about derivatives of all of them, we're talking about derivatives or the function itself, which is just y.
Right. Yeah.
Okay.
So it's a little different for ODEs because in ODEs, y is the function. In PDEs, we're calling the function f, and y is a variable. I know that's a little bit confusing.
Okay. That still makes sense, though.
And so the ones that are out would be this one, and this one, because these things don't have y's. Okay. Any thoughts about that at all? Okay, so I'd like to actually start getting into real PDEs. This first part, I forgot the name of the section here, but it was mostly just an introduction, reminding you what PDEs are, what's an ODE, doing some notation, all that kind of fun stuff. But in the next section, we derive two of the most important equations in PDEs. So one of them is the wave equation, and the other one is the heat equation. And when I say they're the two most important equations in PDEs, I mean, like, most applications that I've seen, people start with either the wave equation or the heat equation, and then they talk about, like, when you're modeling something, you start with the general formulation of one of those two things, and then you tweak it to apply to whatever you're thinking about. So in the wave equation, let me just sort of do a quick background here. The wave equation aims to think about things that are waves. And so obviously like a sine or cosine wave, right? But lots of things, and you can imagine if this was like a guitar string, and you pluck the guitar string and you look closely at it, it would be making these waves, but the waves would be changing over time, right? Like these bumps would be going up and down as the wave bounced. And lots of things do that in nature, which is why this is so important, right? You could think about sound waves like this, or light waves. You could think about actual ocean waves. You could think about the rising, anything that sort of rises and follows that sort of periodic behavior. You can model using that. And so the wave equation becomes really, really important for any wave-like motion. And lots of things have wave-like motion. The heat equation, which is the thing we'll sort of look at mostly next time, the heat equation talks about how heat expands or moves side to side inside of a region. And so when I think about the heat equation, it makes me think about, again, disease spread, because this might be the disease in a region, and when it's spreading, the disease is getting bigger, right? That region is increasing, so it's going outward. And when you're doing a good job of social distancing or whatever, right, then the disease is going inward and the size is getting smaller. And so it's called the heat equation because it's based on how heat flows and dissipates over time. And so that's sort of what this is saying. It's like you'd have some peak of disease in the middle, but then as you move away from the epicenter, you'd have less and less disease moving out to the sides. And so it follows the same sort of dissipation that heat would do if you like lit a candle, right? If you got really close to a candle, it's really hot, but as you move farther away, you can still feel the heat, but less and less the farther away you get. So anyway, that's just sort of the general, this is how we're going to think about deriving these two equations. And again, lots of things in the real world either look like a wave or sort of move in and out the way that heat might, depending on the heat source. And many applications using PDEs therefore use one of these two concepts. So that's my sort of introductory spiel. I think I'm just going to set up this next page rather than trying to work through the next 5 or getting stuck in the middle or something like that. Yeah, I think that'd be good, actually. So let me just set up the idea and maybe extend this concept with this other concept here. Let me do another piece of paper. So, and I actually posted a couple YouTube videos in our YouTube page that do a better job of illustrating this, and I'm probably going to. So if you wanted to look at this again, if you're particularly interested in partial differential equations or modeling, you might want to think about doing this, looking at that video on our YouTube list. Anyway, the video talks about this. It talks about having a string suspended between two people. This is how the wave equation was derived. And let's say we pluck the string, right? So it could be a guitar string, or maybe it's one of those like slack line things or whatever, and you pluck the string. When you do that, it's going to make a wave through the line, right? And we'll assume like this, where the line started is kind of like the ground. It's like the zero state, and then the line is going to raise up some amount away from that sort of initial state, and we'll call that distance u of xt. And so we're talking about more than one dimension, because this thing is going to change over time, right? Like if you pluck that string, it would sort of wobble back and forth and look something like this, but it's going to change over time. And the specific location you're at is also going to change, right? So x is this part, and then time talks about how it's wiggling back and forth. Let's zoom in on one piece of that line. So here I am again drawing that line. We've got the line going through the middle. That's sort of the initial state. And then we pluck it, and it sort of makes a wave, right? Well, does everyone kind of get what I mean by that? I actually should have gotten a rubber band. I used to do this with a rubber band. Let's see if I have a rubber band right here. I do have a rubber band right here. All right, so it's the kind of thing where like we stretch out the rubber band. Let's see if you can see that. And if you pluck it, it happens really quick. If you had a really long, loose rubber band, it's kind of easy to see. But when you do that, it kind of bounces back and forth, right? And it's going to make this kind of wavy looking thing. And there's one example of what the wave might look like, kind of zoomed up close. With me on that? Okay, so here's how the wave equation was derived. This piece of string is moving over time. And so this piece is going to come down this way, right? And this piece in the next instant is going to move up this way. Let's assume that this is like their maximum boinginess or whatever, right? This is sort of where they end up, and then they move back, and they'll kind of go back and forth like that, right? Here are 3 places on the line on this curve. One of them is right at the peak, and the other 2 are off to the side. And let's do a couple more even farther off to the side. Which part of that line is going to be moving the fastest? Like which one is going to have, not moving the fastest per se, but which one is going to have the most force? Which one's going to be sort of have the most force? What do you think?
Part of me wants to say the shorter one because it's traveling a greater distance in the same amount of time, or in a quicker amount of time.
Yeah, so like however far away it is from the equilibrium state, sort of the more force it's going to have, right? So if that was the force of this particular spot right there, then this spot right here is going to have a slightly less force. So I'm going to draw a slightly smaller arrow. And then the ones off to the side are going to have an even less force than that. And the similar thing would be over here. I should have drawn on maybe a steeper curve or whatever, but right. So the farther, sort of the more into the curve you are, the stronger the force is going to be, and the farther off to the side you are, the less the force is going to be. Do you agree? Right? Sort of like you have the most tension up here and the least tension down here. And so in math talk, what we could say is that force is proportional to concavity. Right? In other words, remember concavity from calculus tells you the curvature of a function at a specific spot. And so the concavity at those peaks is the highest concavity because it's the most curved there. Whereas we move away from the edges, it becomes sort of less curved, right? It's farther outside the concavity. And so if we wanted to write that down in math, not mass, but it's going to involve mass, force, we know, is mass times acceleration. And we know concavity. Does anyone remember how you think about concavity when you do calculus? something to do with derivatives, but anyone remember more than that?
It's to do with the polarity of the second derivative.
Yeah, the second derivative, right? So you look at the second derivative and you look at the sign, right? So this one would have like negative second derivative. This one has positive second derivative. But the point is, right, our line is the function u x t. And so if we want to talk about concavity, we take the second derivative with respect to x, because this is the x axis there of that. And so we're saying this expression is proportional to this expression. And we know more about this expression too. So I won't mess around with mass. Mass is just whatever mass is. But how do we talk about acceleration with derivatives? I don't think about that. So concavity was the second derivative in the spatial direction. I don't know about acceleration. So acceleration is the second derivative in the time direction. I'm sure you've heard that acceleration is the second derivative. If you had a function f that tells you position, the first derivative tells you velocity, and the second derivative tells you acceleration, right? And so that's what this is saying, right? So this force equals mass times acceleration is this, m times utt, and then concavity is uxx. And so what we just found is that utt equals k uxx, right? You could just divide this m over to the other side and call it k. And that's what the wave equation is. So let me just pull out the wave equation and show you the final version of it, wherever the hell it is. The wave equation is that. So on a couple of pages from now, this is the wave equation, right? This is the second derivative of u with respect to t, and then some constant squared, and then we're doing uxx. And it's because, again, the force is proportional to the, the force is proportional to concavity. And so we end up deriving this equation in that respect. The c squared part, the fact is, again, it's just a constant, but it turns out to be a positive constant. And so they're writing it as c squared just to show you that it's positive. And it turns out that that constant is like the wave speed, the speed of the wave moving. So the higher that constant would be, sort of the quicker back and forth the thing is bouncing, or the quicker the wave would be moving across the space there. So that's sort of, this is the loose and dirty way of getting the intuition. And then what we're going to do on the next page is actually derive it more carefully. So this is going to be a zoomed in version of the string. And then we're going to break it down into the different dimensional components. And we will end up deriving the actual wave equation in a couple pages from now, right there. I'm not going to do that right now, I don't think. Maybe I'll just relate it to this next image, and then we'll do this to the next, leave this for next time. So that's what we're going to do here. We're going to zoom in on a piece of the string. And so this is like a zoomed in, very small version of the string. And again, we have the position of the string in space and time. And then this is the exact same position of the string, except it's got delta x added to it, right? And so this is like the x, like if this is x, the x-axis down here, for example, this might be x, and this right here might be a little bit farther down from x, right? So x plus a little bit. And so that's what this is saying. It's just the position of the string at different places. And what we're going to do is we want to figure out the tension on the string. And so the T in this case is going to be the tension. And this T down here is the tension on this part of the string. And this T over here would be the tension on that part of the string. And they have different tensions because the string's moving, right? And it might have been pulled in different places. So every sort of location has a different tension. And so what we're going to do is we're going to look at the position of the string over time. Again, looking at the individual components down at the bottom, and we'll eventually derive the wave equation from that. I'm going to stop there, though, and sort of, I think what we'll do next time is try to get through the next 3 or 4 pages. So we'll derive both the wave equation and the heat equation, I hope in the same sitting. It's going to be a little bit maybe tedious, a little bit high level, but I hope you can enjoy that a little bit, and maybe it'll inspire you to take a full-on PDE course. I actually have never personally taken a full-on PDE course. I've taken plenty of ODE courses. I've seen plenty of people present things on ODEs. I've read about ODEs. I've watched YouTube videos on ODEs, but that's not my personal specialty, and I don't, I haven't taken a course in it. So I'm personally interested to learn more, and I enjoy teaching this class because it gives me an opportunity to read a little bit about it. Anyway, can I answer any questions about what we've talked about today? Again, we'll pick up with this, but driving the actual wave equation, I suppose on Thursday. Any thoughts?